All right, can everyone see this?
Yep.
Sweet.
Yep.
Okay, well, welcome to the Software Demo Days series. I'm Megan Anderson. I'm one of the Primer Software Demo team members. Dominic is also going to be joining us later, kind of closing out running the Q&A portion. Swara is our DOE program manager. And Swara, would you like to say a few words before we jump in?
Yes, thank you so much. Hi, everyone. Welcome once again to another installment of Software Demo Days. If you've been here before, if you're coming for the first time, you know that this is where we aim to foster cross-collaboration between various software developers in the marine energy space, primarily on software that we ourselves at WPTO have funded through the years. But today is a little special because MBARI WEC is actually a software that we haven't worked with directly before. And we're just so honored to have Andrew and Michael presenting for us today on the MBARI WEC software. So what is MBARI WEC? It stands for the Monterey Bay Aquarium Research Institute Wave Energy Converter. Now, this was a WEC originally developed in 2009 to provide power to MBARI's various research missions. And it was initially funded by the Defense Advanced Research Projects Agency, or DARPA, basically to assess the availability of wave power worldwide. And basically using Gazebo, this software aims to make a digital twin simulation for a wave environment. And effectively, this allows it to account for the sheer added mass of water in these simulations, making this a particularly large simulation that can provide us with many insights in the marine energy space. But not to get into too much more detail, I'll just give it to Andrew and Michael to explain the rest. And just thank you all so much for being here today. I'm really excited.
I don't know. You're doing pretty well. You can keep going.
I mean, I don't want to steal the spotlight from y'all.
Yeah,
You know.
All right. So can I take the screen? Yep.
In 1 second. Sorry, just have one more thing to show.
Yep.
So like Swara said, we're going to be talking about MBARI WEC today. The next demonstration will be on Wednesday, June 28th, and that will be WEC Up Tool, and we'll talk more about that later. But now we'll be hearing from Andy and Michael about their software.
Great. Well, thanks for that good introduction. I'm hopeful you can see my screen now.
Yes.
Is it true? All right. So I have a handful of slides here, and then we're going to be jumping around windows. We're going to try to keep you organized here. Software demonstration is a pretty tricky task, really. But I'm going to start out with some introductory slides here, talking about the MBARI Wave Energy Converter, the software and the simulator and the actual hardware that's in the ocean. This is a project, as highlighted there, that we've been working on for some time with the purpose of supplying energy for our autonomous platforms in the ocean, our autonomous underwater vehicles and instrumentation. And it's really a recognition that there's a limitation of what you can do with battery-powered systems. And if you want to have extended deployments, you need to, harvest some energy from the environment to make that possible. Here's what we're going to do today. So we have a few plans. One is I have about 10 or 12 slides here to describe the project and outline what this is all about, and provide a little bit of background. And then we're going to switch over and do some command line interactions with the buoy itself. It's at sea right now, sort of out here off our offices. And we have a good cell phone link to it so we can interact with it. And we wanted to highlight sort of what that looks like. And then when we move on to the simulator side, you'll see that it's very similar. Because a lot of the goal here was to make a simulator that really was indistinguishable to the software between the real buoy and the simulator. So we kind of went back and forth about whether we should show the simulator first and then the buoy, or the buoy first and then the simulator. And there's pros and cons to each, but we're going to start with the buoy. And we'll log into that and do some stuff. Hopefully it'll all work correctly. And then we'll move over to the simulator. And I think at that point, you'll start to see the similarities. Then at the end, we can have some questions and wrap up in summary. As I said, the persistence presence problem, this is a slide I've reused before and talked about, but you need a number of things if you want to have instrumentation in the ocean for extended periods of time. You need vehicles that are reliable and capable and do what you need. And they need to be pretty autonomous. Once they're out there on their own for weeks or months at a time, they need to not require care and feeding from shore every single day, sort of exhausting for the people on shore. Instrumentation, depending on the measurements you're interested in, that instrumentation is important. But all of that is dependent on how much energy the platforms have. And you really only have two options. One is you can bring that energy along inside batteries, or collect energy from the environment and recharge those batteries. And there's a very different characteristic here. This is a slide that I've used a number of times. When you bring the energy with you, you charge up the battery and you deploy the vehicle. If you're out for weeks or months, you end up with a fair bit of power, but there's sort of this awful 1/time decay in the amount of average power available as your deployment duration gets longer and longer. These metrics are arguable, but you can see that, the other option is harvesting energy from the environment has a very different characteristic. It's a much more complicated solution, but it does not decay in time. If you're there for 3 months, 4 months, 5 months, 6 months until the system fails or needs recovery, you have that energy available. These are kind of interesting metrics. We'll talk a little bit more. We've done a lot of work with solar and wind systems over the years, and this is sort of a typical metric of watts per kilogram is how I normalize things. And then, of course, the wave energy system is higher, like 5 times or something higher in terms of the capabilities or the amount of energy that can be captured and provided. More complicated as well, so it's not a perfect miracle. But so in those thoughts, I think, as mentioned, DARPA originally came to us and asked us to explore this, and they were interested for 4 or 5 years, and then we took it up and continued the project after that. But the system that has been developed is the MBARI wave energy converter, which is shown there in a photograph on the right before deployment. And it's about a 10-foot diameter buoy. Can you all see my mouse?
Yes.
All right, good.
Yep.
So I'll use that to gesture a little bit. The buoy is about a 10-foot diameter buoy, and then below that hangs this power takeoff device that we're going to talk about in a little more detail. And then 100 feet down, there's a break in the cable there, so this isn't to scale. There's this anti-heave cone or heave cone down here, which resists motion. So the result is a differential motion between the buoy on the sea surface and this heave cone, which is hanging down in stiller water. And that differential motion and force represents the energy that we're trying to capture. So this power takeoff device is a custom designed item here at MBARI, and it's an electro-hydraulic device. So as the waves come and go, the piston ramps in and out of here, spins a generator, which makes electricity, and that electricity gets conditioned in its voltage and sent up to the buoy where it's stored on the buoy and batteries up here. Of course, that's the damping element, converting velocity and force into electricity. There also needs to be a spring in the system. So the upper part of this is a pneumatic spring that resists motion and provides a force that's proportional to the position of the piston. So in operation, it looks like this very rudimentary cartoon on the left. Waves are coming, bouncing this thing around. The downstairs plate heave cone isn't moving too much. And this differential motion and force in and out is representing the mechanical prime mover of the system, which through many steps gets converted to electricity. By comparison, I hinted at this earlier, this buoy on the left is a solar buoy we built here in the 2000s, maybe late 2000s, that we really packed on this size buoy as much solar panel and wind turbine as we could. And that turns out to be about a 5,000-pound system and about 50 watts. This wave energy, this WEC prototype that we're talking about here is also about 5,000 pounds and is 200 to 300 watts on average. So there's your sort of 5x increase in energy capture. And of course, you pay for it in complexity, not particularly cost. It's nothing too expensive here, but the deployment's complicated and it's a little harder to maintain. So that's the promise of wave energy, is that you can generate significantly more power with the same sort of amount of hardware. And really, when you start talking about recharging autonomous underwater vehicles, 100 to 200 watts is the point where it starts to become possible. If you're in a solar-powered system with 30 to 50 watts, you're really quite limited in what you can do in those vehicles. Talk about that more later. Anyway, this wave energy converter is about, like I said, 10-foot in diameter, 200 watts average. We do regular deployments of this system. Here's a little video of the divers. I'm not going to play the whole thing, it's a little long, but give you an idea of the system. It's kind of industrial looking. There's one of our engineers, is also our diver, doing an inspection. There's the buoy, and they're going down just to make sure everything's fine. And you can see the buoy here on the surface, this diagram on the right. Again, I mentioned the pneumatic spring, an important element, and then this generator and converter and the hydraulic motor and the hydraulic. So there's two components in parallel, and then this heave cone down here. So there you can see those components as they die down. Check out the jellyfish there. Yeah, so it looks like that hadn't been in the water very long on this inspection dive, because after 6 or 8 months, it's just totally caked in growth and you can't really see all that stuff. It's just a big seaweed wad, but that doesn't bother. If the seaweed's kind of neutrally buoyant, it doesn't really get in the way of its performance. So. All right, so like I said, we routinely do pretty long deployments on this. This is an example from 2023. We were out for, 232 days, averaging about 200 watts of power. And that power comes in these big gulps of power. So this is the max power recorded in every hour over this 7-month period. And you can see that the max power is often 6,000 watts. So you're getting 200 watts in 6,000 watt gulps. And that's one of the huge challenges of wave energy that probably everyone on this call is familiar with. We get this hourly data, telemetry data coming in. We're going to go into a little more detail on this later, but this is posted on the website kind of continuously every hour it updates, and you can see the last hour of its behavior. Looks like right at the time this was captured, it was sort of at the 47 watt level, so probably a pretty calm day. Some design features of this that are relevant to the simulator and understanding is as I said, the power takeoff device is an electro-hydraulic device. So this piston moves in and out, pumps oil, it's a piston, pumps oil through a hydraulic motor, so the high pressure oil flow turns into rotary motion, which is coupled to an electric motor, which is running as a generator. And then there's a bunch of custom power electronics that take the electricity that's coming out of that generator and converts it to a constant 300 volts. And that's a 4-quadrant piece of power electronics, meaning that it can act as a generator or as a motor. So you can push the heave cone around if you choose to with the control features. There's about a 6 kilowatt hour onboard battery up here on the buoy, and then a bunch of 24-volt power supplies and an Ethernet network and instruments and computers, and a Linux control computer and cell phone connection sitting on the buoy here. I'm going to talk a little bit more about the architecture of the code of the hardware here because it's relevant to the simulator and understanding the code. Another big feature is this heave cone has these green doors. They're not really green, but they're green in the diagram here, and they can be in 2 positions: closed, as shown here on the right, or open. And that's one way we deal with storm survivability. When the big waves come, we open these doors. Actually, they open automatically when it detects big waves, and the water can flow through the middle here and reduce the loads on the system. And without that, you kind of break in the big storms. What you find out in wave energy is the bigger you make this anti-heave device, the more power you make in calm weather. But as soon as you get a big storm, then basically everything breaks. So that's why it's important to have some. I think my opinion is that all successful wave energy converters will have some ability to change their morphology to deal with that wide range of conditions. And you can see that in some of the other successful designs. CalWave, for instance, is big on this idea and others. So that's been kind of a practical realization of this project for me, is that if you don't have some ability to reduce, to visibly shed loads in a wave energy converter, you're probably not going to succeed unless you're in a very calm place that has very regular weather conditions. Yeah, so wave energy is very difficult. When you're talking about a year deployment, you're talking 3 to 5 million wave cycles, and that piston is going in and out every wave cycle, and it's kind of nuts. If you add it all up, how many meters or centimeters it strokes in and out, you're talking several million meters of linear travel of that rod, if you count it back and forth as if you add that up. And finally, and we're going to talk about this relative to the control part of this, wave energy devices are really odd in that we are designing them to maximize the forces, which really is a problem when the big storms come. The situation is that the wave speed doesn't change. You can't really control that. So if you want to capture more energy, all you can do is increase the force, and it means that the forces are very large in these systems. Speaking of control system, the system out there right now, in its absolute default, does a very simple control approach, and that is that it applies a force on the power takeoff device that is proportional to the RPM of the motor. So it's following this program curve, and it's sort of a piecewise linear thing. It looks a little funny. There's a reason it's that shape. But in any event, at any given moment, what that computer out there is doing, the microcontroller that controls the power converter, is it's looking to see how fast the motor's spinning. It says here, oh, 2,000 RPM. So therefore, I better be exerting minus 10 amps of winding current. So it's always, by default, opposing the motion of the spinning motor, and that is the generator mode. It's trying to slow it down, and therefore that means it's absorbing power. So this is the default curve, and we have a couple of parameters where we can shift this up and down or scale it a little bit. But if you don't do anything and the Linux computer on the buoy is off or something, this is what the thing will do. The alternatives, of course, are much more sophisticated model predictive control type things that are really exciting ideas, and have the opportunity to make the device smaller, impose stroke constraints on the system, and increase energy capture and robustness. These things are all over the literature in terms of simulation. Much like the graph I made here in my little MATLAB simulation, you can quickly demonstrate that if you know the waves that are coming in and do the right kind of control, you can dramatically increase the power that's being captured. So in this graph, in the simulation, the mean power blue line is what you get if you do the passive control that I described on the previous slide. But if you do some advanced control, model predictive control in this case, you're going to get potentially a 5x increase in energy capture, which honestly, we don't really need to make more energy for our purposes, but this sort of thing would allow you to make the device smaller and more survivable and easier to deploy and cheaper and all that. Now, it does require that you put energy into the system at some parts of the stroke. So you can see, in this case, the mechanical power absorbed is negative, and that means that we're pushing the heave cone, not just absorbing power every time. So it's really tricky to know when to do this, what control signal to give is in theory very easy, and in practice very difficult. Oh yeah, MPC simulation example. So a lot of what this project is about, that's the background. So we're done with that. A lot of what this project is about is to make the wave energy converter that we have out in the ocean available to other people to develop and test this sort of control algorithm. And to do that, we created we implemented ROS on the Linux computer and provided all the services and data so that a person could write code that we could deploy on the buoy while it's out there without bringing it in and reprogramming it, just like sending it over the cell phone link, and run a new control algorithm based on the measurements that are happening on the buoy and sort of overriding the default passive linear control that I talked about with a new answer kind of thing. So we chose ROS2 to really try to engage a wider group of robotics engineers. ROS is very, very popular in many robotics areas, and has bindings to Python and of course C++. So that was the origin of the choice of ROS, and that's a little double-edged sword in that ROS is a little complicated and takes a learning curve to use, but does have a lot of capability. Of course. Oh yeah, so I want to back up here slightly and say, the reason that's possible is the architecture of this system. As I mentioned, there's a Linux computer that lives on the buoy, and then there's these microcontrollers that really make up the heart of the system. And those microcontrollers don't do much. They do the minimum thing and the safe thing. So if this Linux computer turns off, all of these microcontrollers, there's one in the battery, there's one in this what we call the spring controller, and I'll show some data from that. The main one is the one in the power converter that takes a command. That's the one thing that's measuring the RPM of the motor and deciding how hard to resist at any given moment. And then there's one in the heave cone, which is responsible for opening and closing the doors and make some other telemetry. Those are all linked up on a CAN bus, controller area network bus, telemetering data to the Linux computer. But I want to really reiterate that if this Linux computer fails or turns off, these things keep doing the right thing, and the system behaves in its default mode. Similarly, we believe that these microcontrollers are all smart enough to not take bad advice. So if the Linux computer or the program written on the Linux computer says, oh, do this, and it would be damaging to the system, these microcontrollers down here will say, yeah, thanks, but no thanks. So that's what gives us confidence to sort of open up the control space to other people that aren't us or do more risky things with the system. And here's a diagram of the setup. This is the buoy Linux computer that has, you can ignore the radar driver, that was part of a different project, but it has a GPS driver and it has the shore comm processes that we'll see some of in a minute, has some oversight processes, and it has the possibility for advanced control where it's telling the power converter to exert a force on the PTO, whatever the advanced control algorithm decides is sensible at the moment. Of course, there's also drivers that listen to all this data that's on the CAN bus. So remember I told you the microcontrollers, there's 4 of them that live here. There's the batteries, the spring controller, the power converter, and the heave cone controller. They're all communicating with this Linux computer over this CAN bus. I'm hopeful that that's clear how this architecture is. This is the same diagram on the left in the deployed system. But of course, you know, it isn't really practical to write a bunch of code and upload it to the buoy and hit go and hope for the best. So this project built a simulation environment that is really intended to be a digital twin of the system that behaves in the same way from the point of view of the software. That's a lot of what we're going to demonstrate here today. And so basically it's all the same stuff, a Linux computer, but we replaced this hardware, these microcontrollers, with a dynamics and controller software simulator and simulated C-state generator. And the goal is that this advanced control algorithm here cannot tell if it's running on the real buoy or on the simulator. That's our dream. So to implement that simulation, we use Gazebo, which is another open robotics product, and it worked out pretty well for us. It's fundamentally a physics simulation that computes the equations of motion in 6 degrees of freedom of rigid bodies that are connected by some elements. We had to create some new code that would simulate our exact pneumatic spring, our electrohydraulic PTO, the free surface hydrodynamics, and the flexible tether. Those weren't really components of the simulator, so we added those. And interestingly, for the hydrodynamicists in the group, this type of simulator is really geared towards terrestrial robots, so nobody cares about the added mass. But of course, in the marine environment, the added mass, that is the mass of the water that it gets accelerated when your underwater robot accelerates, is kind of significant, like major. In our case, it's a huge number. So we really needed to have a physics simulation that included that. And we were able to work with Open Robotics to add that to this capability. So that's an outcome of this project. Is Gazebo now is one of the few robotic simulators that properly includes the added mass contributions. We're proud of that. And as I've said a few times now, while running, the ROS interface provided to the user software is exactly the same between the simulator and the real buoy. And of course, there is additional information that's only available in simulation, like the incoming waves. So that's made available in the simulation, which you can use to cheat, I guess. So this is a diagram of the simulator in action. I'm not going to spend a lot of time on this because we're going to run it here in a minute in a live screen and sort of see what happens. But it's got this other features that come along with this type of simulator, these fancy graphics and rendering, which are kind of nice to look at. In the end, you don't end up using them that much. And as I've said, what we really wanted to do is engage the possibility of outside researchers to use this platform. And that's where we've kind of struggling. We haven't gotten as many people involved as we would have liked. We got some, and we have some on the horizon. And part of what we're doing today is trying to show this off and spread the word. Anybody here on this call, certainly welcome to contribute and get involved. We would love it. So, or if you know somebody. Anyway, we are aware that researchers, like when I got personally, Michael Anderson was like a ROS expert when he came, but when I got into this, I was new to ROS too. And there's a little learning curve, but we've really tried to make the system approachable and implement using the simplest solutions we can. And we've built up these tutorials and examples, which we're going to go through today, and then made some easy access using GitHub features. And there's a discussion forum. Yeah. So that's some of the screenshots. I'm not going to spend much time on this because we're going to go to the live thing here in a minute. Documentation there. There's the documentation site. I'm going to show this in a second. Tutorials. The tutorials we think are pretty important, and that's what we're going to do in the demo here today. And there they are. Okay, so that is the project overview. Now I'm going to move on to, before we get to the simulator and running through those tutorials, we thought we would start with a live demonstration of the buoy software itself. The buoy is at sea right now. And I'm going to go through that, and then I'm going to hand it over to Michael, and he's going to show a little more details. So can everybody still see my screen? Yes?
Yes.
All right, thanks. I'm not looking at my own screen, so I'm not, if you guys all drop off, I probably won't know it. So. Okay, so this is my command line interface on my computer here in my office, and the microcontroller, or the Linux computer on the buoy, is called Torque. Nobody knows why. And there's a user named buoy, so if we SSH in there, it'll ask us for the password, which I'm not going to tell you. And it'll log us into the buoy there. So that is the sort of splash screen of the buoy. So what I've just done here is logged in from my computer here to the Linux computer that's living on the buoy about 10 miles from my office here out to sea there. And I'm going to do it twice. So I have two windows. And this splash screen includes a few things that are helpful to remind us how to use the thing. But what I'm going to do is change directionally. You know, what's happening is this buoy is running all the time and logging about 25 channels of telemetry at 10 hertz. And if we go to this, you'll see that every time it reboots, it makes a new directory. And if we go to today's, you'll see that every hour it makes up a new file and zips it up. So the one that isn't zipped up is the most recent one. So if we look at the size of that file, we'll see that it's growing. So every time I do that, it's going from 308.8 to 308, 309, 310. And if we sort of display that file in real time, we'll see that this data is in text format, CSV file, and sort of sliding by at a rate that really can't be read. But you see the first character is a 0, a 1, a 2, or a 4, or a 3, and that is representing each of those different microcontrollers. So if I narrow it down to just the, just say well, let me give you the best example, the spring controller, you can see that this is the data coming off that spring controller, which has a few components. One, it has a load cell that's measuring the load under the buoy. And I know you're going to ask why it's negative 4,884 pounds. And the reason is that failed on the day after the deployment. So that should be reading like 3,000 pounds representing the force below the buoy, but that thing has failed. So we're just going to ignore that. When we get to the simulator, you'll see that it has not failed in the simulator. But the next column is the piston position. And this is in inches, and it's a very calm day out there today. So it's oscillating back and forth at 16 inches, 18 inches, 20 inches, 21 inches, like that. And the next two are the gas pressures. Remember I said there was a pneumatic spring involved, so there's these gas pressures that are being measured, and then there's some other telemetry here that we don't need to worry about. If we were to look at so you can see that the piston's oscillating up and down, and if we were to look at the power converter, again, we get the identifier of the power converter. It happens to be number 2, the time in like Unix time. And then the next column is the RPM. So you can see as the waves come and go, the RPM is going up to 1100 RPM, down to minus 800 RPM, back to 0, back and forth. The next one is the bus voltage. So you'll notice that when the thing is spinning, it goes higher, converting power. But going back to the spring controller, you can see this is the position. Now, there's a bunch of command. The way we interact with the system is using this collection of commands, multi-call command power buoy dispatcher. So there's one executable on this Linux computer that can send a variety of different things. And the one that I'm going to do a little test with here is PC bias current, this one here. And what that does is it adds a current to the, remember I showed you the piecewise linear relationship between force and RPM, or current and RPM, it adds a number to that. So if I add a positive bias current to that, like 14 amps, what's going to happen is it's going to have the tendency to pull the piston in. So right now you can see that this is sitting at 19 inches, but when I execute this, that's pulling up 9, 8, 7. Yeah. You know what just happened is we got to the end of the hour, so I have to redo. There it is. That's the next hour. It zipped up the file while we were talking there and started writing in a new file. Okay, so we'll try again here. So you can see when I issue this bias current, the range has gone to 0 because it's physically in the ocean, pulled that piston all the way up to its maximum extent there. And this is timing out after a moment. If I have to keep entering this command as I'm doing right now in order to keep that piston up. We actually do this once a week to scrape the biofouling off the hydraulic rod. I did it a couple times this week because we were practicing this yesterday, but you can see I mentioned that the controllers are smart enough that if they get a bad advice, they'll go back to normal. So this command I'm sending has a timeout of about 10 seconds. So I just sent it. And after about 10 seconds, it decides that I've fallen asleep or I've lost communication with it or something, and it will fall back down to its normal position, we're hoping, after about 10, 12 seconds. Yeah, there it goes. So now it's going back to its normal default mode. So the reason I'm showing all this is to highlight that we do have control from this Linux computer of what's happening on the buoy. And, you know, we can also, I've done it here using the keyboard and the command line interfaces, but we can do it programmatically through the ROS interface. So I'm going to turn this over to Michael now, and he's going to show us some of those details about how it works on the buoy, the ROS interface. And then after that, we'll go to the simulator, and you'll see hopefully that it's pretty similar. Michael?
Hi there. So I'm going to show you that oh, I need to share the screen, sorry. Can you see the screen?
Yep.
Okay, so I'm also on the buoy right now. And all the data that Andy's just showed you is also available on ROS2, so we can see a list of topics. We have the battery data, power data, the spring data, and we have a set of, so all the commands that Andy showed you, we also have as ROS2 services. This has a few ROS specific things, but the main ones are that Andy showed you is the PC winding current command. Oh, sorry, the bias current. Yep, bias current, and we can actually call that like this. We can do a ROS2 service call for that topic and this message type, and with a bias current 14. And we can actually subscribe to any one of these. And we can see the data coming out. Might be a little hard to see. We have the RPM going up and down, the battery and winding currents, and we have the voltage we're generating. We can also plot all of this data on a nice tool called Plot Juggler. It has ROS plugins. And right here we have the rangefinder from the spring controller. That's the piston position. We have our AHARS Z velocity of the buoy float, the RPM of the motor, and we can do a custom series where we can do some math. It's Lua based, and we can see the power generated and 5 30-minute averages I've done here for power. As you can see, it's a pretty calm day out there right now. And then I'll I wanted to go over a few notes for installing the simulator. Sorry.
Yeah, let's go on to the simulator. I think maybe we could wrap up the first section there with a note that, what you've seen here is us interacting with the buoy at sea. And I've done it the old-fashioned legacy way with the CSV file and the command line. And Michael's demonstrated that you can do all those same things through the raw system, which, although we've demonstrated it here as doing it through the command line, it can all be done programmatically from within a piece of software. And that's the power that the ROS brings to us here. And so I just want to make clear that distinction, and then we can go on to the details about the simulator. And installation is always a problem, so Michael's going to touch on that.
Yeah. And if anyone has installed the software, we'd love to hear about your experience with that and how we can make that easier, or any issues you had. And then, oh yeah, so installing the simulator, we have a couple tutorials. And I'm going to our documentation site, and if you're installing from source, right now we use Ubuntu 22.04 with ROS2 Humble and Gazebo Garden, and all that is pretty straightforward. There's many very good ROS tutorials for how to do all of this, but we've laid it out for you here to work with our specific simulator. And as a note, I have been working on upgrading to Ubuntu 24.04 with ROS2 Jazzy and Gazebo Harmonic, and that should be coming soon. For the Docker, there's a few requirements here. Install Docker, and then we need to do the post-install steps so you can run Docker as a non-root user. And it really helps if you have an NVIDIA graphics card and installed NVIDIA Container Toolkit for OpenGL rendering instead of software, hardware rendering instead of software. It's much faster, nicer to look at. And so there's a few steps you have to do there. And I also wanted to point out that we have pre-built Docker images on our GitHub, and in our MBARI WEC main repository, we have some helper scripts to run those. You can also build from our Docker file, which is also in that repository. We have some helper scripts for that too. We've really tried to make it pretty easy to get started. And Andy can show you how to do that.
Right. Hopefully. Well, actually, I'm not going to show you how to install it because that's hard, but I'll show you how to use it. Yeah, but the point being that there's two different ways to install it, kind of equivalent, and it's a bit of your dealer's choice whether you want to install it from source or from Docker. Okay, so you're going to drop it and I'm going to share now. Is that how we're doing it? Yeah, cool. Okay, so now we're going to go, I'm kind of on going to bring in another computer here, I hope. Okay, so this is my Linux computer that I'm showing. Can everybody see it okay? So
yep.
the tutorials here, we just kind of ran through. We didn't want to spend much time on installation because it takes a while and it doesn't seem the best use of the time. Hopefully people can install. But what we did want to do is run through a few of these tutorials that kind of take you from zero to being able to do it in executing this code. So starting with running the simulator is the first step. And it says here, step one, source the workspace. So this is a small annoyance of ROS, is that you have to do this overlay, source this setup bash file in order to make everything work. So that is something you have to execute each time in every new window that you open. So here on the right, I've opened 3 different windows. And I have a note at the end of this tutorial, notes on workspaces, that describe this problem and this issue. In fact, if you're just a user and you're not doing any software development, you can put it in your bash RC file so that every window you open has it done already, and then you never have to think about it again. The reason Michael and I don't do that is it does seem to interfere with the build process of the software. Since we're the developers, if we put that in our windows, then we have a hard time opening a window that doesn't have this interfering thing. I think ROS is getting a little better at making that smoother, but at the moment it's kind of become habit for us to source it individually in the windows. So, okay, that's hopefully the worst of the annoyances. So to launch the simulation, it's launched from ROS 2. So this is the gazebo simulation that we built to do this. You can copy this like this, but Michael put a lot of work. So if you copy that to the clipboard, it takes everything but the $, which was no small feat for Michael to execute. So that's the thing that starts the simulator. And it's a little verbose and it's nonsense that it puts out there, but hopefully the simulator starts and you can see, kind of like the animation I showed before, the buoy floating on the water, the power takeoff hanging below, and the heave cone down below that. Right now, it's at time t = 0. It has not started. It's just sitting there waiting to start. And the way you start it is, says here, after you've launched it, the gazebo rendering of the buoy system should become visible. Yay, it did. And then the next step is to start the simulation, press the play arrow in the lower left. So that's this one. And the waves start there and it starts bobbing around. You can see it says 99.57%. So it's set to run at real-time speed, clock speed. So it's not accelerated at all. This, I guess, blue or gray patch represents the local tangent plane of the incoming wave surface. We didn't put a whole lot of work into rendering the incoming waves as much as we would have liked to. So you get an idea of what's going on with the water going up and down, and you can see the buoy is moving relative to that water line. The water line of the buoy is going up and down. The piston's stroking in and out here due to the heave cone falling below, and it looks like I started it. The default start is with the doors open. You can see the gaps in the heave cone there. So while that's running, it's kind of now the rest of this Linux computer I'm working on is an awful lot like the at sea buoy. For instance, if we go to the files that are being created, the log files, remember I did this on the buoy, this file is growing bigger and bigger, 57.3, 600, 500, like that. And if I tail it, you can see that again, it's the same type of CSV file with the same data coming through, 0, 1, 2, 3, and 4 for the different microcontrollers and data sources. And what I'm going to do here is I'm going to just pick out, pick one, the spring controller. And we should see very similarly before, we have the controller ID, the Unix time, and the load cell's working. Because it's the simulated load cell never breaks, it doesn't. So the load cell is showing on this simulator because it is the simulation that's not broken. But the next column is the piston position stroking in and out in response to the simulated incoming waves. And then just like on the buoy, it's the spring pressures and some other status values and interesting numbers that aren't that interesting for today's discussion. So hopefully you get to see that the behavior of this simulator is very, very similar to the buoy. Looking back at the next tutorial here, just like on the buoy, not only is the legacy command line stuff implemented, but the ROS messages are too, of course. So we can, just like on the buoy, list those. And what we'll do is, it looks a lot like it's supposed to. And then what we're going to do is we're going to say ROS to topic echo. So that's the list of topics, and each topic has a bunch of data in it. And now we're going to list the spring data because that's what we've started to enjoy looking at. And you can see that the rangefinder here and the load cell and the upper PSI and the lower PSI. And you're going to notice that the units are changed. The load cell is now in newtons, and the rangefinder is now in meters. And all we can say is we're really sorry. We made an effort. ROS is very sort of SI oriented, so we made an effort to make our ROS messages kind of BSI, but of course our CSV files are imperial oriented, and it doesn't look like we stuck with Pascals here. These are obviously in PSI, so it's not a perfect miracle, but the data is there. And hopefully that you can see that just like on the real buoy, the data is in each place. There's a tutorial here that explains how to start, install, and start Plot Juggler so that you can make a very similar graph that Michael did on the buoy with the buoy data against the simulator. I'm not going to do that because in setting, I'm kind of between computers here. My usual workstation is out for repair, and in setting this up, I reinstalled Plot Juggler, and it seems to be struggling some package management problem with Humble, this version of ROS. So that's something we need to look into, and I think we're very close to going to the next version of ROS with our software in general, so that should clear that up. But I don't know if anybody else, put it in the chat if you had any problem running this, installing this Plot Juggler, because I certainly did. But we're going to skip that for a minute. I'm showing the data log here going on, streaming by, and again, I'm back to the CSV file because it's a little easier to understand in inches than in meters, and it's buoys bobbing up and down, and it's oscillating. The next tutorial here is the implementation of PB command. So much like on the buoy, in the simulator involved, the same command line implementation is here, and you can do a lot of the same commands. So it says the same multi-call command power buoy dispatcher, and some commands are supported in simulations, the one that makes sense. There are a bunch of commands that exist on the buoy that we don't support in simulation, like the bender. You don't know what the bender is. The bender is a ground fault detector that measures whether there's a connection between the 300-volt bus and seawater. Well, there's no real merit in simulating a ground fault, so we don't simulate that. But we did include those commands in this simulated version of this command so that you can see them there. It just says unsupported commands. So what we can do is watch this, and in the simulator here, I will again do a PC bias current 14, just like I did on the buoy. And with luck, it'll start to retract the piston. It has the same timeout behavior, so I have to issue this again and again. And you can see that in this window here, the piston is mostly fully retracted. Of course, the waves are still coming, pulling around. So all I've done is added a sort of force to pull the piston up, but the waves occasionally overpower that force. So it's at 0, and then maybe it bounces off an inch or so every now and again. And the spring pressures change accordingly, and the load cell doesn't really change too much when you do that. But it has the same behavior if I just wait here for a moment. I think it's on a 10-second timeout. Eventually, the simulator will behave the same as the controllers on the buoy and decide that I'm out to lunch and go back to its default behavior. And the result is the heave cone will drop, and there it goes back to 13, 14 inches. It's not going to work very well on this rendering machine, but if you have a little better graphic setup, you can zoom in on this piston. I'm hoping it works. Yep, you can zoom. You can zoom in on the piston there. I'm lost probably. Yeah. And well, maybe we can do it. So you can see the top of the pneumatic piston. We kind of made the housings a little transparent in the rendering. So you should be able to see that move up a little when I issue this bias command, and you can see the piston moving to the top of the range there. Hopefully that's clear to everybody. So that piston is now fully retracted in the simulator, much as it did at sea. And then after we wait for our timeout, it changed here on the numerical display, but it also changed in the rendering. And after a minute, you'll see that fall down. Let's hope. Gotta wait till it's in the right spot. Yeah, see, it's falling back down to its normal sort of quarter extension. So that is a lot of what I wanted to talk about. Oh, there's one other detail. So this is cool, right? To have this rendering, and you can see the piston move, and it's really fun to look at, and it's almost entirely useless for doing real work, because what you often want to do in a simulation world is like batch up a whole bunch of jobs and and start them running much faster than real time, and go to sleep or go out to dinner or something, and then come back and have the results. And that doesn't lend itself to running this in real time with the display running. So there is another way to execute this software, which is also in the last tutorial here, adjust simulator parameters. And I describe here that when running a simple instance of the simulator, this is the simple command that we executed there. But there's a whole bunch of parameters that can be set at startup: the duration of the simulation, how big the numerical time step is, what the C state is, the phase random seed, a bunch of different things. And sometimes you want to just cycle through a whole bunch of options. And I'm going to make this a little bigger. And you can see that we have a YAML file of, what does YAML say? Yet another markup language file that highlights all these different parameters that you can set: the physics time step, the state of the door, open or closed, the scale factor, that's a scaling factor on that linear damper, battery state of charge, because the electronics need to be simulated a little differently for an empty battery versus a full battery. And then, of course, interesting to everybody here is going to be the wave state. You can specify a monochromatic wave state with an amplitude and a period, or a spectrum. And there's two options for this spectrum: this standard Brett-Schneider spectrum, where you specify significant wave height and peak period, or alternatively, you can put in a custom spectrum. And we'll talk about why we have that. So you can specify frequency versus power, wave power, across whatever range you want, and it'll run those. But I'm going to demonstrate this here in this window called Batch. I made a simpler, well, actually, I have an example in the tutorial of a very simple YAML file that has less of those options, and we'll show that. And I put it in here in my directory before we got started. But you can see that duration, that's in seconds. So I'm just doing 3 quick short simulations because I'm really just trying to demonstrate how the files get generated more than doing real work. This is an interesting one. The seed is the random phase. Whenever we simulate these wave spectrum, we always have to assign a phase to each component of the wave. And there's 2 options. One is just let the computer do that randomly every time it starts, or you can specify the seed that you like so that you do 2 runs and you get the same exact time domain wave profile. And that's what we're doing here, 42. You can enjoy that joke if you want. In this case, we're running the real-time factor of physics at 50. You can set it as large as you like, and it will run as fast as your computer is. Enable GUI. This is a good one. Turn that off because it's not that great to look at. Physics time step. In this case, 10 milliseconds seems to be a pretty good number. We've done a bunch of sensitivity studies, accuracy versus time step, and we don't really see much reason to run faster than 10 milliseconds. Scale factor. So I have 2 scale factors I want to run in this study, and then 2 wave spectrums. One Brett-Schneider wave spectrum at a 2 meter significant wave height and 14-second period, and a 4 meter wave at 16-second period. So you can see we have 2 scale factors, which is how hard it's resisting, and then 2. So there's 4 actual runs. So if you go here, it gives you more instructions in the tutorial. It reminds you to source the thing, which is always a pain, but I've done that already. So in this case, we're going to use this command. Put it here, and we'll walk you through this command. There's a bunch of stuff you don't have to worry about. ROS2 uses a launch file system, and there's the package and the launch file name. But the most important part is we're saying sim parameters YAML file equals irregular waves.yaml. So that's this file that I just ran through. So when you run that, it'll run through those 4 different cases at 50 times real-time clock speed. Well, maybe 50. It depends how fast the computer is. My faster computer that's in for repair right now will run at hundreds of times the real-time clock. This one might be a little slower because it's a borrowed one. So that should be done in a moment. And then the question is, where did it put all the results? So at the end, somewhere in this message, it'll tell you what it did. But if there's a thing in the tutorial that says finding the output, and the output gets put in this batch results 2025 06 04 11 56 45. So that's clearly a timestamp, June 4th, 2025, right now. And we make it a little easier by having a symlink to the latest batch results. So you can just CD to the symlink. And if you list it there, you'll see that those are the 4 runs. And if you look at this, it keeps a log of that, so you know what happened. Batch runs, maybe I have to make this wider for everybody to see. Let me try it again. Yeah, so you can see that those are the 4 runs it did, the start time, the file name, where it put it, where it put the answers, and then some all those parameters. Remember we had, here's the 2 wave spectrums that are repeated for each of the scale factors, 2, 4, 2, 4. And then if you were to go to any of those directories, for instance, this one, you'll see more directories which have the output of the CSV files. Looks familiar, hopefully, at this point. There it is. So then we also have some tools that really aren't in the website to, this is what we did. When we really wanted to test the simulator, in my closing slide, I show some of the details about how well the simulator behaves. And we had to run hundreds of jobs because we have a wave buoy out there making energy. We have a wave measurement buoy next to it. So we knew the wave spectra at any given moment. And then we had a half hour of captured data from the sea. And then we wanted to run a simulation with the same parameters, the same spring settings on the buoy, the same input wave spectra, and compare the results in some statistical way. So we ended up having to run hundreds and hundreds of cases to do that. And of course, this batch file system was very useful for that. Any questions at this point? I hope that it's understandable. I know it's really hard to go through watching me keyboard away and understand what's going on.
Just anticipating one question, the log files generated faster than real time are actually written as real time, even though the simulation runs faster than real time.
That's right. That's a great point. So the results in all cases are written out with the start time being the time of the day here in the world that the simulation started, and then it runs, the simulation time runs forward from that moment, I think, right? Yeah. Good point. The faster than real time thing is great. And this is one of the fastest simulators I've ever worked with. And we did a lot of coding at a low level to make that possible with the Gazebo plugins, and made a lot of choices around fidelity trade-offs versus speed. And there are spots here and there where we could have gotten a little higher fidelity, but it would have been an enormous cost and speed. So during the development of the software, we were doing a lot of study on that to see that we were staying a little bit sane, and we didn't want to end up with something that ran super slow. Okay, so I again took you through the running the simulator from the command line tools, how to start it. Now, the big dream here is that a person, and we've done it internally, and we've actually had external people do it as well, it's not quite as much like, is to write software code that runs on the buoy and executes in the background and takes over for the default controller that the power converters are doing right now. So I can turn this back over to Michael, and he's going to show you some of the tools that we've set up to make that hopefully a little bit easier. There you go, Michael.
Okay. Can you see my screen?
I can.
Okay. So yes, I'll start walking you through some steps here to start adding some controller code. And we've really tried to make it as easy as possible just to insert code here and start having some fun. And as I mentioned before, you've seen before, we have several ROS2 messages and services to interface with the buoy. And we've really designed the simulator as a digital twin so that when you're writing control code, they can't tell whether it's the real buoy or the simulated buoy. And so we've designed an API to help make all of managing the ROS2 infrastructure a little bit easier. And we've really built the simulator so that you can play around, and once you've written some code there, we can be reasonably confident in how things will work on the physical buoy. So I'll show you some. Oh, let me get,
I guess we have about 15 minutes, Michael, and then we can leave some time for questions and such.
okay.
Yeah.
So we have a bunch of ROS2 messages and services, and we actually have some documentation about that in the ROS2 interface section up here. And I'm going to just briefly look at that. We have a description of all the messages and their types and the topics that they're on here. Going back to this page, we also have Python and C++ API, and we've got some documentation for that also up in the ROS2 interface. The key part of this API is that we've handled a lot of the ROS backend for you, and when you inherit our interface class, there are several callbacks you can overload, and when you overload them, the presence of them being in your class will cause the interface in the background to subscribe to topics and bring data to you at that function. So if there are any that you want or don't want, just have them or don't have them. And then the other part is that all of the services, the ROS2 services, we've set up as functions. Just call these commands, like the bias current command or the winding current to set torque for the linear damper. And there's a C++ interface as well that is very similar. So I'll just be walking you through the Python interface to create the linear damper. So like I said, we've tried to make it super easy. We even have a GitHub template for you to get started. I'll just navigate to that. That tutorial down here. And the template is on GitHub. I'll just go there. Interesting. Well, I'll just show you this. There should be, oh, I think I see it. No, something's different. I'm sorry. So normally there should be a button up there to just use this template. Something's wrong with GitHub right now. So you just click that and you create a new repository. So it's not a fork, it's your own repository to do whatever you want with. And you can call it whatever you want. And there's, you would put it in your ROS workspace and clone it, the usual things. And you'll have a structure that looks like this, just a normal Python ROS2 package. And then there's a couple places, you can also refer to the README for this information in that repository. There's just a few places in this tutorial we've highlighted where those things need to change in different files. This is a package.xml is telling ROS2 that this is a ROS2 package. ROS2 uses setup.py, not like a pyproject.toml or pep15, 517 if you're familiar with that. There's just a couple places to modify to customize it for your purposes. And there's also a YAML file that is a ROS that helps you define ROS parameters for your node. At the end, you should have something that's customized. I'm just skipping through a little quickly because we're running out of time, but that you'll have basically a skeleton of a controller with a control policy for you to fill out. You can define any variables or dependent variables on those parameters, and then this would be your target, and your control code would go here. This would be giving you feedback, and then you would return what you want to update. in the system. And I'm sorry, I'm skipping through a little bit, but in the outer control class, that's where you would define, do the ROS2 thing, declaring and getting parameters from your YAML file, and then calling your policies update params. And so this is all available in that template repo. Here we've defined the power callback. That means that the interface would subscribe to the power data topic and provide you that feedback data here. For instance, for the linear damper, we require the RPM, and scale and retract are damping gains. Retract is an additional multiplicative gain in the retract direction. And then we would update the winding current to control the damping torque. You can also do some open loop logic in the main function. This handles the ROS2 loop. And there's just a note here about the functions that are available and the topics that are available, and you define these callbacks or don't to get this data. One more note is you can set the feedback rate of the power converter or the spring controller. You can go up to 50 Hertz. And then if you're using the simulation, you would want to use SimTime, or if you're on the physical buoy, you would just not call that. And then there's notes here about building and running, and if you have tests defined, you can test those. And this should be what you would see if you just ran the thing. And then, so I'll walk you through the linear damper tutorial next. It's basically it's already running on this is what's running on the buoy by default, as Andy mentioned. But we're just showing you how it works and how you can do something similar. I should mention that this tutorial, this tutorial is completed in the MBARI WEC template. I'll just navigate there, and you can look in the linear damper example branch, and this is what it would look like if you completed all the steps in the tutorial, and you could simply run it. So to do the linear damper, the control policy needs the torque constant for converting our winding current to torque, or our desired torque to winding current. We need the RPM breakpoints for our linear piecewise linear damping function, and the torque breakpoints for that function. So we define those parameters in the controller YAML, and we define some of those variables in the control policy, and there's some defaults. We would need SciPy to interpolate our damping function, and then we update some dependent variables on those parameters, like the current. We would get the current from the torque and the torque constant, and define our interpolant damping function. And then down in the controller, we would declare and get those parameters into the policy class. I like to just print out how it's configured for logging. And so next in the controller, we would define the target, what we want as feedback. We want the RPM and our gains, damping gains. We would get the winding current that we want from our interpolated damping function, apply our gains, and return the current. So in the controller, all we need is the power callback to get that data, and so we get that data, and then the interface does that for us. It passes the data to us here, and we pass that data to target, get our winding current, and we send the command winding current. And then don't forget to instantiate your control policy and set parameters and set your feedback. And then we can try it out. Actually have, sorry, 1 second. Actually have the buoy running. It kind of wandered off a little bit.
Yeah, that's an interesting point. There's no anchor modeled here, which is a really small part of the dynamics, so we didn't bother with it. But if you let the thing run for days and days, there's some very slow drifts, and it gets kind of off your screen eventually.
Oh, I'm sorry. So I can actually run that. I actually have that pre-made here. And we can run that linear damper. So our winding current is a function of RPM, the scale and retract factor, and here we're outputting what that winding current should be, and that's going over the ROS2 service, the command, to the buoy, and that's actually controlling it right now. And as Andy described, it's already doing this, but we can override what it's doing, and it'll happily take that if it's not going to destroy anything. And then once we stop that, it will have a timeout, and it'll continue doing what the microcontroller wants to do. And I think I think we wanted to have some time for questions.
Yeah, that's great, Michael. Thank you for showing that. That is exactly the illustration of the ability to, it just kind of happened there in simulation. It would happen the same on the buoy, where you start a piece of code, an executable on the Linux computer, and it now starts sending commands to the microcontroller. The microcontroller says, well, okay, if you want me to. And it does that until you kill the process. And then 2 seconds later, after that timeout expires, the microcontroller goes back to its default behavior. So it's a great example of why we're sort of confident in having people that maybe aren't us, or even if it is us, running code that we haven't tested in the lab and this sort of thing, just download over the cell link onto the buoy at sea. The buoy at sea is sitting out there about 9 months of the year now, so we don't bring it in very often. So we needed a facility to be able to make these. In order to experiment with any kind of control stuff, it is very handy to have this type of ability to upload code to the buoy, hit go, see what happens.
And we have used this API. We've played around with it for various things. So the trefoil doors will automatically open if the piston extends too far, and that's done with this API as well.
Right.
So we're also using it.
Yeah, for sure. All right, happy to stop sharing screen. I got one more slide, and then we can do we have 15 minutes for questions and other discussion. So,
okay.
Who would have thought we were going to be on time? Can you see my screen?
No, not yet.
Really? I screwed up then. Hang on. Oh. Now?
Yes.
All right. All right, so that's what we did. I went through the project overview here, general terms, then we demonstrated the interactions with the buoy at sea, and then demonstrated the interactions with the simulator, which hopefully look pretty similar. Talked a little bit about how to code it, and then we want to have some time for questions here. But I do want to say that we last year, looks like the date's missing from this preprint, but we released a paper in which we took data, and I touched on this about the batch file stuff. We had a SOFAR spotter buoy data running next to the buoy for many, many months, and we took wave spectra at any given time off that buoy and then ran that wave spectra through the simulator and compared across a reasonably wide range of period and significant wave heights, and tried to make an assertion in a statistical sense how well the power converter and the simulator was doing replicating what was actually at sea. And that did uncover a bug in our simulator because it was like forever making twice as much power in the simulator as it was at sea. But in fact, that allowed us to find that bug, and it wasn't, in fact, just a typo, and fix it. And after doing that, the things started to look pretty good. So this, you have to do some kind of statistical measures here. So the upper, well, I mean, let's cut to the chase. The mean thing is how much power was it making, right? So the correlation here on the right hand, the bigger graph here, the right-hand graph is the average power being measured in the field experiment versus the average power being measured created in the simulation using the same input wave spectra and setup of the buoy, doors open, doors closed, that sort of thing. And we did it for Gazebo and WEC. Dominic and the gang at Sandia built a WEC model that was very similar, and it also performed very well. But you can see we were quite happy, honestly, with this correlation, considering the wild environment of the ocean. You can see that their blue line is our Gazebo sim, and the red line is the WEC sim, and the comparison there. We also did some other measures here on the left of the RMS piston velocity. Was the piston moving at the right speeds? And was the motor moving at the right speeds? And again, you can see good correlation there. So this really gave us a lot of confidence that we got the coding right on the simulator. Pretty pleased with that. And finally, we do have this discussion forum, issues, WEC GitHub issues. That's what we're using, and we're really interested in having people put material in there that we can respond to for everybody to see. And if you don't want to do that, you can just email me or email Michael, and we will get back to you immediately, because we're very supportive of people trying to use this software. So from there, I have a whole bunch of extra material and interesting things, but instead of that, we can do some questions.
Yes, any questions from the audience first?
Come on, y'all put your cameras on.
Andy, I have a question about how you kind of balance the control strategy with reliability of your WEC.
Yeah.
Because like generating a lot of power is not really, like, too much power seems like not that useful to you, but it is really valuable if your WEC is reliable. Like, how do you kind of ride that line?
Yeah, there's a lot of dimensions of that line. Right now, we're only using about a small percentage of the power we're generating. So, we can kind of program it to leave those doors open more often than not, because it doesn't wear the system out as fast if the doors are open. That's an option, right? Once the batteries are full, there's no point in making more power. So in principle, you could use this, kind of write some code, the simplest thing, right? Just, the battery's full, open the doors. And that reduces the wear and tear on the system. We don't do that now because we're kind of interested in wearing it out. And, that's the only way we find out the reliability issues. And, we've really benefited from the benefit. We've been really lucky to be able to deploy this system for a dozen years straight or something and break it a lot and then fix it and gaining reliability that way. But that's an example. I think the control strategy itself, the fancier techniques, model predictive control in particular, can deal with constraints. Don't ever let the piston go out further than this far. And that would be a wonderful reliability gain if you could do that sort of thing. The thing we really don't want is that piston hitting the end of the stroke. That if you could make the stroke bigger in this system, you could soften the spring constant and get the system closer to resonance and make more power and have higher reliability. But the problem is it just becomes a little too big to deploy. So we're dealing with these practical ship size restraints and that kind of thing. So I don't know. I hope I answered your question.
Yeah, awesome. Thank you.
Any other questions?
Yeah, I had a question. Sal here from Enro.
Yeah.
So your low-level control, does it have some inherent constraints that override when edge cases come? And how did you make sure that they're all compatible with ROS nodes and the overall ecosystem?
Yeah. So the controller, we believe we haven't tested every possibility, but we believe that the microcontrollers that are doing the power conversion now and loading the system will always do the right thing. For instance, you can't send a ROS command to have it slam the piston into the end of the rod, because the microcontroller is sitting there kind of noticing and won't do that sort of thing. So, you know, what we have probably not tested every possible constraint. And the one thing we haven't done is, like, if somebody got in ROS and did some kind of denial of service attack on our microcontroller where it just sent commands at a bloody high rate, I think it should be okay, but I haven't really tested that, you know. So there are probably cases where you could get a little crazy, but we haven't broken it that way yet. So I hope I'm answering your question, but we really worked hard to let the microcontroller always do something smart and not, I don't think you can break it from the Linux computer commands. I mean, it's not to say that I go crazy with the Linux computer commands in the middle of the winter when there's huge waves and my trees are bending over my house and stuff, you know.
What do you say to folks who would be critical of the Raspberry Pi, like not using something more robust as your local sort of?
It's a little bit of a habit. I mean, at the moment, it's there's no reason we couldn't do something else in there. All it's doing most of the time is logging, and it suits our needs for that. But yeah, if somebody came along and wanted to do some machine learning thing and needed a Jetson in there or a bigger computer, we got the power to power it. We got the network. It's all there. It would slot right in. So we're super happy to implement something like that.
That's cool. Well, thank you, Andrew.
Yep, sure.
Yeah, Andy says that he doesn't think we should go crazy with commands, but his favorite thing is up arrow enter up to try to break my code.
Yeah, that's right. That's how I break Michael's code, is I type as fast as I possibly can.
In your experience, have you guys found that ROS is pretty reliable? Like, has it ever crashed on you guys or anything like that?
Michael's best suited to answer that one. You've used it here in this project and elsewhere. So,
yeah, I think there sometimes things happen. One quick, easy thing is that ROS can heal itself. If something not too pathological happens with a node, you can just respawn it with the launch files. There's just it'll automatically respawn. And then the nature of the network connectivity is pub sub. So and it's data driven. So if there's no data, nothing happens. And once data comes, it starts working again. So unless like there's something seriously wrong, like one or two hiccups shouldn't be too big a deal. But that's just in general. We haven't really noticed too much of that in our system. We've worked out a lot of those bugs, I think.
Do you have any hard limits on the refresh rate or update rate, baud rate, that kind of thing?
Yeah, the microcontrollers are set at a certain rate. Andy can talk to a little bit more about what happens if you flood them, but I don't know if
the telemetry data coming up from the buoys are set at a default of 10 hertz. From all the microcontrollers are streaming synchronously at 10 hertz. That, honestly, is pretty fast compared to the 0.1 hertz wave. But you can set those up to 50 hertz, I believe, or 100 hertz. And this system's 50 hertz. We can set that up to 50 hertz, and that's a command you can send. There's a raw service to increase that, so you can crank that up to 50 hertz. These electronics are used in a different system at the University of Washington, and they wanted faster yet, so we ran it at 100 hertz there. I haven't really, again, that's a case where I haven't tried to find the limit, because I don't really think there's much reason to go faster than 100 hertz or 50 hertz. So.
Thank you.
Can you guys speak to maybe the level of development effort required to do all this work? Are we talking, I'm guessing this is a multi-year, multi-thousands of hours of developer time to develop this? Hey,
we're going to take that as a compliment,
Yeah.
Yeah, we can. It's the first 2 years of this project. It was a 4-year effort graciously funded by the Department of Energy. The first 2 years of that was software development. That was in the plan. And we had a subcontract to Open Robotics Software Foundation to kind of contribute their expertise to this. And that really worked great for the first part of that, because Louise Poubel, perhaps some of you know, was involved in this project, and she was, I don't know, she did the work of approximately 8 to 10 people, it seems. So it was a little hard to say, but she then moved on to Zipline, and we got a little less benefit from open robotics at that stage, and Michael and to some extent myself took over the bulk of the work at that point. But I think it's 1,000 hours, probably, maybe half a person year of work to create what we did here. What do you say, Michael? About right? I mean, a lot of late nights, of course, but that was fun.
Yeah.
One piece of the software development, we had to implement the free surface wave body interaction solution, which is really the simplest Cummins decomposition linear free surface stuff, based on added mass and damping coefficients versus frequency, converted to the time domain and impulse response functions convolved with the recent motion of the buoy. That really didn't exist in the gazebo world, but we created it as a separate library that's actually my personal GitHub account, for better or for worse, but that we broke out, and this project that you're looking at here depends on that library. And we did that because at the same time we were hearing from Sal and what's the other guy's name, Sal, that was working on the Kronos system, and they were saying, hey, we might need something like that. So there's definitely a separate software library that is a kind of general purpose agnostic to ROS situation that does the wave body interaction solutions.
And there's Python bindings for that too.
And Python bindings for that too, yeah. Thanks to Michael.
All right, so I know we're almost right at time now. If there's any other questions, feel free to voice them now, or you can contact Andy and Michael after the call. I'll take over, wrapping us up.
I will say that.
Oh yeah, go for it.
Maybe I can just interject one thing. We're super interested in helping people use this system. We're here. Currently, we're still funded by Department of Energy to support this project and have people participate. We have a couple people on the horizon that from Oregon State and University of Washington that have a project planned. We, of course, in our brains have a few ideas of how this could be used to do interesting projects. I'd be happy to talk to anybody that likes, or students that kind of need a project idea. I think I could give them. I should probably post some of those project ideas on our documentation site. But we're here, and this buoy is becoming, this wave energy converter is becoming a more and more central part of what we're doing here with repowering our autonomous underwater vehicles. We have an autonomous underwater vehicle program that has underwater vehicle docking for repower that is going to be integrated with this wave energy converter next year, and then running science missions forever, hopefully. So this buoy is going to be in the water, hopefully a while, and continue to operate. So even if and I guess when the Department of Energy funding ends, this is everything you've seen here today is in the open source world, and we're going to continue to support it and make it available to people if they want to use it. So it's not going to just disappear if Department of Energy funding, wasn't re-upped or whatever. So, okay, all right. Thanks.
Thank you so much. This is a lot of great information. Just wanted to throw a reminder out to everybody that the next session is 2 weeks from now. WEC Op Tool is the next session for the software demo days, and that one will be using CoCalc through these few slides, just to have them in the recording to show them really quick. That's just an interactive software for being able to run the demonstration as it's presented to us. And so here's some instructions. You can send the email you used to create your CoCalc account to Kelly at this email. I can see in the chat right after presenting. So you can be prepared for the session, and just have your computer ready with some internet connection, and be ready for the next demo day. So thank you so much, and thanks for attending. Hope to see you next week, next session.
Thank you for organizing these. I think they're really good.
Yeah,
thank you so much for presenting.
Thanks everyone so much for attending, and yeah, Andy and Michael, thank you so much. This was brilliant to watch, and I think we all learned a lot today.
Okay, we're here for you if anybody wants to get involved.
Awesome.
Bye.
See everybody.
Right. Thank you all so much. Take care. Bye.
Thank you. Bye.